Hello, everyone. Mr. Minnick's my name. Math is my game. Today, I'm joined with my favorite Algebra 2 class ever in the whole wide world. My second period class, when they watch us back, they're going to be like, that's not fair. My fifth period class, if they watch that back, they're going to be like, that's not fair. That's not nice. Should I comment on that? I'm going to hold my comments. I'm going to hold my comments. We'll tape lessons in those classes at some point, I'm sure. So you might ask yourself, who are all these people on the board? You probably know one of them, maybe two of them, maybe three of them. If I had to guess which ones you all know, and I'm assuming that by you all I'm talking about high school students, I would assume that many of you know who he is and who she was and who he is. How am I doing? So up top here, who do we got? Charlie Sheen starred in that one show, 2.5 Men. And then the queen of fashion, the late Joan Rivers, the late great Joan Rivers. And down here, probably most notably known for his VMA performance last year, Robin Thicke, right? So anyway, so if we look at Charlie Sheen for a minute, does anyone know who this cat over here is? Is it okay? Can I say cat? Do you mind? When I say cat, that's my Warren accent coming out. I'm just talking about people, guys. So here's Charlie Sheen. Who's this guy? It's his dad. And what's his dad's name? Well, his dad's name is Sheen. This cat's name is Martin. So this is Martin Sheen. And he is Papa, right? He's Charlie Sheen's Papa. I like it when you call me Big Pop. And over here we got Charlie Sheen, right? Okay. Charlie Sheen. And he is the is it S-O-N, son? Okay, he's the son. Well, we'll come back to that other dude in a minute. Let's go down to Joan Rivers here. So, of course, everybody knows Joan. Joan Rivers. And who's next to Joan? What's her name? Is it Melissa? Okay. Melissa. That's my wife's name. And of course, this is Joan Rivers' daughter, who I think isn't she kind of taking over the business, the family business and the show and all that stuff? Okay. Is there a resemblance between Joan and her daughter? Let's go down to this last one here. So we know who Robin is. I actually have an uncle named Robin. Robin, T-H-I-C-K-E, I think is how you spell their last name. So who's this over here? It's his dad, and what's his dad's name? He was actually in a show with Kirk Cameron back in the day called Growing Pains. Anyway, I'm really showing my age now. His name is Alan Thicke. Okay. Do they look alike, Alan and Robin? Okay. Who's more attractive, do you think, Alan or Robin? Robin's not a bad-looking guy. He needs to shave a little more often, I think, but that's a personal thing. All right. Well, let's look back up at the topic again at the Sheens one more time. Now, nobody knows who. Well, maybe you know. Anybody know who that is? Yeah. What is it? The coach from the Mighty Ducks. He's been in a lot of movies. He was actually in The Breakfast Club too, if you've ever seen that. Now this one's kind of weird because everybody knows that Charlie Sheen has the same last name as Martin Sheen, so you assume they're father and son, and they are. But nobody knows this dude's name here in the middle. Well, anyway, his name is Emilio, and that kind of sounds like, not to sound like stereotypical or anything, but it sounds like some kind of Latin name, right? Like maybe Mexican or something. Wait till you hear his last name. His last name is Estevez. But he is Martin Sheen's son, and I think he looks more like Martin Sheen than Charlie Sheen does. So Emilio Estevez and Charlie Sheen are brothers, and their dad is Martin Sheen. Everybody get that? Okay. You probably never knew that. I think they're full blood relatives. A lot of actors and actresses change their names. A lot of times they change their names. If you ever do like a Wikipedia search on anybody, like an actor or actress, not that Wikipedia is the most reliable source, but most actors and actresses change their names. Okay. So anyway, what we're going to be talking about over the next, I don't know, over the rest of the class really, whenever we graph, we're going to be talking about parent functions. Okay. So that's kind of how we're going to introduce this. It's parent functions. Now, if you think about parents, you probably say, well, they're cool. No, they're not cool. I like them. No, I don't like them. I'm not here to comment or speculate about your relationship with your parents. But if we think about the definition of a parent, we're going to relate that to a function and come up with a really good definition here. So to avoid any kind of getting too far off topic, I'm just going to go ahead and say, is it fair to say that a parent function would be a function, whoop, I can spell. We're going to define it this way. It's a function from which, and you might say, well, why do you do that? In the English language, if you've made it this far in English, I'm sure you probably know it's not cool to end a sentence with a preposition. So that's why we put the from which next. A function from which others are born. If you think about parents, parents in theory have children. The children are born to their parents. Hence, a birth certificate has birth parents, father's name, mother's name on the birth certificate. So we're defining a parent function as a function from which others are born. Does that seem reasonable? Does it make sense? Okay. Good. All right. So, again, it's a function from which others are born. And again, just to reiterate the language here, how come I didn't say a function others are born from? Because it's not cool to end a sentence in a preposition. I try my best not to. It's not cool. Everybody all right so far? Well, what I'd like to do is I'd like to look at some really neat functions. The sine function. It's actually S-I-N-E, sine function. In the Cartesian plane, it's a great looking function. Every time I hear somebody say the adjective or adverb, whatever, it sounds like something you spray up your nose. I've been talking about that, but like I've been having sinus trouble lately. Anybody else? In the stats class the other day, we were talking about histograms and antihistamines. But anyway, sometimes people will call this a sinusoidal function. A sinusoidal function. A sinusoidal function. Maybe you've heard of a sine wave. Anybody ever hear of a sine wave? A sine wave. So I'm going to call on Audacity for this one. This is going to be cool. So the sine function, we'll see what it looks like here in a second. I'm more familiar with the older version of Audacity. This is a newer one, but let me see if I can do this. I'm going to generate a tone. Look at that. The waveform is sine. You see that? Isn't that pretty sweet? So 440 hertz, that should be audible by most of us. Most speakers should be able to pick that up. Okay, it's probably something like you've heard on a hearing test or something like that. Now, let me see if I can change the effect now. Okay. Rather than making that 440 hertz, I want to take that down to something where most headphones can reproduce, and that's about 60 hertz, okay? 60 hertz. This is where we get BASS, the bass. That sounds like boom. That's really cool. Here we go. All right. Most headphones can reproduce that frequency. Well, people spend hundreds, even thousands of dollars on headphones that can go down to frequencies in the teens of a hertz. You know what's weird about that? Speakers can't reproduce frequencies that low. You can't hear frequencies that low, but people spend hundreds of dollars on headphones that go down that low. So if I were to play this back, not that I will because it could damage my speakers, but I want to go down to like 5 hertz, okay? And do you see a wave starting to take shape there? Might be kind of hard to see. So anyway, let's go to the graphing calculator because it might give us a better perspective on this. So we're going to look at the sine wave. If we think about a wave goes up and down and up and down. It has troughs. And what's the top of a wave called? It's like toothpaste. It's like a crest, yeah. They still make crest toothpaste? Okay. So the bottom of a wave is called the trough. The top is called a crest. If you take trig, you'll study that. We might actually get to trigonometric functions and graphing them this year. So here's my TI Inspire. One of these days it's going to be all set for me. I'm going to graph a sinusoidal function. Here it comes. Trig. I said trig. Well, sorry about that. Let's try that one more time. Trig. There we go. Sometimes my computer goes a little haywire. I think it's Bluetooth interference, probably from somebody's phone, but that's okay. We'll deal with it. So there it is, the sine function. Everybody see that? Any questions, comments, concerns, short debates about that? Well, it's the sine of x. And it's weird because the pattern repeats over and over again. So it starts here, it goes through the origin, 0, 0, and it repeats this cycle like this over and over. So let me see if I can get my smart board to work with me here. So if I clone that, it repeats that cycle over and over and over again. Okay, it's called a periodic function. Now, what we could, and I know that probably bothers some of you that those lines don't connect it. I'm sorry about that. But so this is a periodic function. Let's go back here for a minute. Martin Sheen and Charlie Sheen. How do they relate? Do they look alike? Okay. What about Martin and Charlie? Do they look alike? So, in theory, if we think about functions, the baby functions should look something like the parent functions, right? Well, watch this. Let me graph another sine function. Let me graph another sine function. The sine of x minus 2 pi. Now we expect it to look the same, right? In the case of Martin and Charlie Sheen, they look the same. Charlie Sheen, or I'm sorry, Martin Sheen and Emilio Estevez. Let's forget about Charlie for a minute. Nobody wants to. I don't want to talk about Charlie. Martin Sheen and Emilio Estevez. I think Martin Sheen lives in California. Like a lot of retired actors live in Burbank, California, for whatever reason. I don't know. It's kind of like the Florida of the West. Burbank is. A lot of retired actors, actresses live out there. Okay. Emilio Estevez, as you might imagine, doesn't live at home with mom and dad because he's been in movies. He was in Mighty Ducks and probably made a small fortune in some of the movies he's been in. And he actually has an Uncle Joe that, well, I better not tell you what Uncle Joe does. Anyway, Emilio Estevez, if I had to guess, he probably lives in the desert somewhere, okay? So Is the desert anywhere near Burbank? No, but it's just to the east of it, right? Just beside it. Why does he live in the desert? Maybe because he doesn't like the hustle and bustle. Have you ever driven in rush hour traffic in Streetsboro? Imagine driving in rush hour traffic in LA. 9 lanes both ways, bumper to bumper. 3 miles an hour. A 6 hour commute to go 7 miles. Do they drive what through the sand? I don't know if he's got a Porsche. I'll bet he drives a Toyota Tacoma. So anyways, we would expect this to look the same, right? But it might just be slid over a little bit because it's the child function, right? So it's going to move to the east or maybe to the west. To the west of Burbank, though, would probably be in the ocean. But let's see. Let's see. Oh, it didn't move. Actually, that still lives at home. Let's change it a little bit then. Let's try that one more time. Let's make that not 2 pi, but let's make that pi. And now it moved to the east a little bit. How's everybody doing so far, okay? Any questions? Now, real quick, because I don't want to give away my secrets here, because we're going to talk more about this on tomorrow. We're going to look at Charlie Sheen now. So we'll take Emilio Estevez out of the picture, and we're going to look at Charlie Sheen. How do you reckon Charlie, other than the black hair, how does Charlie compare to Martin? Anybody ever see Martin in a movie? Martin's about 5'8". And Charlie, you've probably seen him in movies. He's about 6 foot. Just a little bit taller, right? So sometimes we're a little bit taller than our parents. So what do you think? Do those two functions look the same? They look similar. One's just a little bit taller, right? Could I make the one that's a little bit taller move out to the East Coast? You bet. Check this out. Let's move it out to the East Coast. Ready? Let's move out to the East Coast. So it's a little taller and it moved out to the East Coast. How are we doing? So they look the same, right? If you go back and trace the roots, they're the same basic thing with a few modifications. Is that fair enough? Is that clear? Good. Well, we're going to be doing the exact same thing with functions. So we've seen a sine function. Let's look at the most basic of basic linear functions, okay? So the parent linear function, We skipped over something that in years past I spent about 6 weeks revisiting chapter 2. That's all about lines. And I'm going out on a limb this year, making a big assumption that we know just about everything there is to know about lines. So, hopefully today will reveal that you do in fact know that, most of that stuff. So we got y equals x. That's it. Now it's always nice to have a table of values. So here's our table of values. X and y. And it's cool because the y is actually found by whatever x is. That's the definition of it. So I don't know if you remember how to make a table, but we randomly choose these. We randomly choose some x values. And a lot of times we like integers just because they're easy to work with. They're easy to graph because the coordinate plane we usually see goes from -10 to +10, right? But ain't nobody got time for that. Let's just go to -2 and -1 and 0 and 1 and 2. Okay, and that'll give us enough points, I think. So if the x is -2, then what's the corresponding y? -2 also, good. And if the x is -1, what's the corresponding y? -1. And if the x is 0, what's the corresponding y? 0. And then 1 and then 2. Everybody cool with that? Okay. Maybe we ought to graph this, eh? Now, I'm assuming that all of you have passed geometry because that's the prerequisite for Algebra 2 is that you have passed geometry. So let's lock this in place. So we got the point -2, -2, -2, -2. Bam, -1, -1. How many points do we need to make up a line? 2. That was one of the first postulates in geometry you had. Any 2 points comprise a line. Through any 2 points, there's exactly one line. Remember that postulate? Okay. So we technically have enough points, so let me get my line tool. Here's my line tool. I'll make it red. Hopefully that turns out. Boy, that doesn't look so good, does it? That does not look so good. That's a little better. How's that? Better, but not quite. How's that? Is that good? Good. All right. So that's the parent linear function. Everybody with me so far? What's it look like? It looks like a line. What's that mean? It's straight. What's that mean? Well, it goes to the left and it goes to the right. Fair enough? So let's extend this page and let's get some ideas here. Y equals x. Its slope equals what in this particular instance? Anybody got this? Let's take a trip down memory lane. We had this form called slope intercept form of lines that was y equals m, which is the coefficient of x and then plus b, right? So what's the slope of y equals x? I know somebody knows it. Yeah. It's m, which is the coefficient of x. So if we look at our given equation, the parent linear function, let me get my magic marker here. If we look at this, we're looking for x's coefficient, and that's what the slope is of this. So what is it? It's hard to see because it's not there. Yes. It's y equals x, but I'm looking for the coefficient of x, the number before x, the number that's sitting in front of it. Yeah. Thank you. It's a 1. It's not there, and it's kind of hard to see, but it's the 1 that's not there, right? It's going to go away in a second. So the slope there is 1. The implication of that is that the rise over the run factor is always the same. It's 3 over 3. It's -2 over -2. It's 1 over 1. However you want to look at it, from one point to the next, let's see. Get that magic marker going again. I like this magic marker. It's so cool. So if I start at this point here, and if I go down 1, 2, 3, if I go down 3, then I would go to the left 3 and end up right there, right? Everybody down with that? The slope concept makes sense? All right. Well. Anybody know how Darth Vader and Luke Skywalker are related? Luke, I am your father. Right? Seriously? True? Yes? Okay. So if we think about this, y equals x. Whoop, that's going to go away. Sorry about that. Y equals x goes uphill. Is that fair enough? So a lot of times we think of the force, let the force be with you, as a positive entity, as a positive thing, right? Well, what happens if we have Darth Vader, the dark side? Yeah, it's going to go downhill. So let's look at those on the TI Inspire here. So let me insert a new problem here. Doc, insert a new problem in another graph. So here's y equals x, and then I'm going to graph y equals -x on the same graph. So you can clearly see that the one goes uphill, the other one goes downhill. But, whoa, don't want to get carried away there. I do want this label to be up here, there. So I need to get back in there and make that This is pretty cool. My computer is acting the fool today. It's all good though. So there we go. Oh, that kind of looks like the Millennium Falcon a little bit, doesn't it? Doesn't it look like one of the ships? Hold on a minute. There's a Star Wars ship that looks like that. Let's go to Goggle. I know it's been a while since I've watched Star Wars, but I'm pretty sure that there's a Star Wars ship that looks like that. Let's do a Google search. We're going to look at Star Wars ships. Maybe it's not the Millennium Falcon, but there is some kind of ship that looks like that. Star Wars ships. The ones that have triangle-shaped wings. Not this one. I might have passed one of them. I don't know. What's this planet-looking thing? That's the Death Star? Well, it's definitely not that. What's this one? Here's one of the ones I'm thinking of, maybe. I don't know. Like this? Like this kind of. I don't know. It looks like a Star Wars ship to me, though. It kind of reminds me of Star Wars. Is everybody cool with the fact that those are related? They look similar. One's fighting for good, one's fighting for evil. Is that clear? Okay. Well, let's change this up a minute. Is Luke related to Yoda in any way? He's not? And is he related to Obi-Wan Kenobi? Well, that's not going to work then. I guess we'll have to try something else. All right, let's go to the next one. The parent absolute value function. We skipped a significant portion of the first 3 chapters. In chapter 1, you would have graphed this, but we didn't. It goes like this. Y is the absolute value of x. Before I graph it, who can guess what I'm going to sketch off to the side? Not Star Wars. Not Charlie Sheen. I can't sketch him. What are we going to have off to the side? Yeah, here we go. Here's a nice little table. 4 legs. It's kind of like the ones at the restaurant, right? They always tip. Not that kind of table. Oh. X, and then Y, which is found by the absolute value of x. And again, we randomly choose some x values. So -2, -1, 0, 1, and 2. So what's the absolute value of -2? The absolute value of -2 is, I think I heard it, 2, good. And the absolute value of -1? And the absolute value of 0? 0, and the absolute value of 1? And the absolute value of 2? Hey, they're always positive. No, they're not, because 0 is neutral. So let's see if we can't graph this one. Lock that in place. So the lowest point on the graph got a special name-o. We're going to define that today because we really need to. And it's not Mike Jones, and it's not Emilio Estevez, and it's not Martin Sheen, but it does have a name. So we got 0, 0, we got -1, 1, we got 1, 1, -2, 2, and 2, 2. How's everybody doing? Okay. So I'm going to need a ray tool to graph this the right way. So we can go like this, and then like that. Everybody all right? So that's the parent absolute value function. It's the absolute value function from which all others are born. So there's a question, do I know how the graphs can be slid right or left? I do know how the graphs can be slid right or left, and we're going to be talking about that on tomorrow. Was your question about that? What would the function end in? We're going to discover that on tomorrow. Okay, it's a great question. You can read my mind. You know where we're going. Everybody cool so far? Good. Well, well, well. Let's define something. The vertex. Whoop. That looks pretty cool, actually. The vertex of a function is the highest or lowest point on the graph. Now, a long time ago in a land far away, you were taught that you're not supposed to assume, but we do need to assume something here. Assuming there is one. If we look back at a line actually doesn't have a vertex because a line extends infinitely forever in both directions, and it doesn't have a highest point or lowest point because it goes up to infinity and it goes down to negative infinity. So a line doesn't have one, but an absolute value certainly does. An absolute value function certainly does. So by definition, the vertex of a function, is the highest or lowest point on the graph, assuming there is one. We doing okay so far today? Okay. Well, I'd like to show you a baby absolute value function and a parent absolute value function. So here we go. Insert another problem. Insert a graph. The parent absolute value function. I could actually type ABS. I don't know if you knew that, but absolute value of x. Bam, there it is. Everybody all right so far? Okay. Now, here comes the baby function. Do we want the baby to be good or evil? Evil baby. Do we want the baby to be bigger or like taller or shorter? Short, little, because it's a baby. You know what kills me? Is people, not literally kills me, but what cracks me up? What cracks me up is people say, we're having a baby, and then so the day of, they're like, oh, we had our baby. Oh, yeah, what was it? It was a little girl. Of course it's little. What else is it going to be? It's a baby, right? Yeah. It's a little boy. It's a little girl. Here we go. So we want it to be shorter, not as tall. So let's go like this. And tomorrow we're going to talk more about these things. So I really shouldn't show you too much of this today. But is it going to move to the east or to the west? Or is it going to live with mom and dad? Well, it's a baby. Shouldn't it live with mom and dad? That's an orphan? Oh. We're going to the west? We're going to the west with it? Okay. Now, is it going to live to the north or to the south or directly west? I'm hearing north. Northwest would be, yeah, northwest. It's going to be, whose baby's name is Kanye West's baby? So it's northwest. So we'll make it north also. There we go. Here it is. So does it look the same? Hold on a minute. Does it look the same? Does it look generally the same? Hold on a minute. An absolute value function, this blue one, the blue one is V-shaped, right? Okay. Is the red one V-shaped? Oh, come on. Is the red one V-shaped? It's V-shaped. It's just an upside down V. Thank you. And we made it evil. We said it's an evil baby. And we said it's moving to the north and to the west because it's Kim and Kanye's baby. It's northwest. And it's a little shorter because it's a little baby, right? Everybody with me so far? Does this all make sense up to this point? Okay. Where's baby's vertex at? We could calculate that, and we'll talk more about this in the future. It's going to be its maximum point, right? Uh, so baby's vertex is at negative 2, 3. That's kind of interesting. That's kind of interesting. Are there any questions about anything we've done up to this point? Okay. Well, here's the moment we've all been waiting for then. This is where we're going to be graphing the parent quadratic function. Now, the cool thing about knowing the parent function is if you know the parent, you know the baby. If you don't know the parent, well, it's kind of hard to know the baby. If you ever want to find out about, I shouldn't say this, but so if you're dating a girl, just look at her mother, and that's how she's going to be in 20 years, okay? I'm not, is that exactly what it's like? Not quite, but it's pretty close. My wife's name, her nickname I call her is Little Debbie, because her mother's name is Debbie, and I call my wife Little Debbie, because she's a lot like her. Anyway, I better not go too far off topic. Y equals x squared. That's what it is. Has anyone noticed that the parent functions are pretty basic? If you think about your parents, my dad never got a haircut. He always wore just jeans, t-shirt, and a pair of tennis shoes. Unless he was going to church, and then he wore pants, t-shirt, and tennis shoes. But let's look how basic they are. Absolute value function is just y equals the absolute value of x. The linear function is just y equals x. They're pretty basic, aren't they? Okay. So this one's pretty much the same thing, right? Just the bare essentials, because that's how parents roll. So here comes our table, x, y, which is found by squaring x. In that table, do you mind at this point if I go ahead and just get rid of that y equals and just say that the second column is just going to be x squared? Does everybody get that second column is for the y values? Okay, I hope, because we're going to use this a lot going forward. So we'll pick negative 2 and negative 1 and 0 and 1 and 2 again, because those are nice. And what happens when we square negative 2? Most people square it wrong on their calculator, believe it or not. But wait a minute, how can people square something wrong on the calculator? Watch. Negative 2 squared. A negative 2 times a negative 2, a negative times a negative is supposed to be positive, right? You got to be careful how you square this, and I saw somebody do this wrong yesterday. It's negative 2, the quantity squared, so it's really 4, isn't it? Okay, so we get 4, and then how about for the negative 1? It's a 1, and the 0 is a 0, and the 1 is a 1, and the 2 is a 4. I almost made it another 2. It's a pretty sweet looking 4. So, I'll be honest with you, the nice thing about these, the really cool thing about these is this, and I wish I had a better cover up, I'll use this purple one. I really don't even need to worry about those because of something that you study in art class. What? Art has to do with math? Yes, watch. When things look the same on the right as they do on the left, that's called what? It starts with an S and ends with a Y. Because of symmetry, we don't need those other ones. True story. True story. Okay. So here comes our graph. Let's lock that in place. So we go through 00. I was like, oh my gosh. Okay. 00. And then 1, 1. And then 2, 4. So there's 00. There's 1, 1. There's 2, 4. And I said we don't need those other ones because of symmetry, because it's the same on the left as it is on the right. But if we wanted to look at them, here they are. Right? Negative 1, 1, and negative 2, 4. Hey, wasn't the absolute value function symmetric as well? For the most part, I think it was. So here's where people get this wrong when they graph. There's not straight line segments that connect these. It is a curved, smooth curved line, and it's difficult to graph sometimes, but it is a continuous curved line. It's not little individual line segments. And when you graph these on the graph paper that I'll be supplying for you to graph these on, um, please don't use little straight line segments. Who can tell me what OO is, other than what Usher likes to say a lot? It's the origin, but it's also in the context of the fact that it's the lowest point on this graph. It's the vertex. So the vertex is at 0, 0. Now, we did say that this thing is symmetric, right? Because of that, and only because of that, I'm about to draw a line here. There's a line that goes right through here. I drew it so straight by using my line tool. So let's see. Let me make that nice in green. Whoa, not that. Well, that's okay. I'll roll with it. Now let me undo that. I better not. I want to make this line. Green and a little bit bigger so we can see it. That line has a name. Because the graph is symmetric about that line, sometimes we use the word axis, like axis of powers, but it's called the axis of what? Doesn't that make sense? People say math doesn't make sense. It makes perfect sense to me. It's called the axis of symmetry. Now, how many of you plan on taking pre-calc in the future? Anybody? If you take pre-calc, when you talk about the axis of symmetry, it is a line, and lines aren't defined by numbers. Lines are defined by equations. Vux hoi. Vux hoi. It's a vertical line. It's a vertical line. It's a vertical line. The x-coordinate of the vertex is the point 0. And this is a vertical line that goes through the vertex. What do you suppose its equation is? Vux hoi. Vertical lines have an undefined slope, and their equation just has an x in them. What do you suppose the equation is of this axis of symmetry? Anyone? Vertical lines just have an x in their equation. It's a vertical line. How about x equals some number? X equals 1. Good try, but it's a vertical line that goes through the vertex, and the vertex has coordinates 0, 0. So x equals 0 is the axis of symmetry. Okay. 2 more things, and then that's it. I know this has been a long lesson. It's probably not one of your favorites, but anyway, it will lead us into Chapter 4, Section 1 beautifully. One final bit of information, the domain, all the x values that are possible. Let's use interval notation. Let's use interval notation. When we graph this, there's little arrows on the ends of the graph. What's that mean? It goes on how far? On the lowest end of the x-axis, it would go to negative infinity, and it would go clear out to positive infinity. We can't get to infinity, so we use the parentheses. If we're talking about the range, what's the lowest y value that this thing has? The lowest y value it has is that 0 right there, right? So I want you to realize that the y coordinate of the vertex has something to do with the range. So the range goes from 0 up to where? Infinity. Good. It's been real. It's been fun. I hope it's been educational. I hope everybody has a great day. Shout out to the future Mr. Minnick. Shout out to the other classes. Mr. Minnick was just playing when he said his first period class is his favorite. But he still likes his first period class. Have a great day. Good.